Okay, before we start the lecture, just a few words about the midterm. I have talked to the other sections instructor, so we decided to cover the midterm until the previous lecture, basically first order differential equation with the integrating factor methods. I did cover a little bit on the separable equation, but that won't be part of the midterm. Okay, yeah. But even separable equation, that's a very simple case. Okay. In terms of the lecture, for my case, it's lecture 1 to lecture 15. In terms of assignments, it's assignment number 1 to number 4. And tutorial, I think up to this week's tutorial. Okay. So, just like the other course, when you prepare for midterm, start from assignments first, and then, of course, maybe start from lecture notes, okay, understand the material, practice through assignments first, and also look at tutorial examples and examples in lecture notes. Once you're done with all this, there are some additional exercises will be uploaded to the Canvas, and you can exercise. But those are the additional. If you have time, you do it. If you don't have time, you don't have to. Okay. So the assignments will be sample questions for the midterm exams. Okay. Yeah. For midterm, we're going to have 2 rooms, this room and the APSC 140 room. We will distribute a student list associated with the classroom. So not necessarily this class student will be in this room. So we'll evenly distribute among the 2 classrooms. Okay. For midterm, there's no formula sheets. You don't need a calculator. Okay. No cell phones, of course. Final, we might consider to give you a formula, but for midterm, so far you don't need. I don't think you need a formula sheet. Okay, yeah. So that's midterm. It's going to be next Thursday evening for 2 hours. And as we planned at the beginning of the term, we're canceling this Friday's lecture and next Wednesday's lecture to compensate for the 2-hour midterm exams. So basically, after this lecture, you have almost a full week, no lecture for this one to prepare. Okay? Yeah. So while you're enjoying Thanksgiving, don't forget your midterm. So unfortunately, okay. Any question on the midterm? We're good? Okay. So let's continue on differential equation. We have covered 2 different types. One is linear . So we have covered linear first order differential equation. We have also covered another type called separable first order differential equation. Okay. So each type you use a different basically approach to solve for this differential equation. Right. Sometimes the same differential equation, first order differential equation, actually can be solved, okay, using either technique. They could belong to maybe linear and separable at the same time. This is one of the assignment question, so I'll quickly go over this. dr over d theta equal to b times dr over d theta cosine theta plus r sine theta. So let's say if you have an equation like this, okay, how do we solve this, right? So what we can do is we can do a little bit simplification, because you got dr d theta on both sides of the equation at here. So we can move all the dr d theta to one side, okay, and then group them. Okay. So if you move this term to the left side, okay, you have 1 minus b cosine theta dr d theta equal to b times r times sine theta. So that will be simplification. And once you get this, and you can clearly see, you could write dr over d theta equal to b times r sine theta y minus b cosine theta. And that actually is a separable equation. Okay, so this r here, okay, this is r here. If I put the r, separate them out, okay, so you have essentially two parts of the function here. You have a function of theta, and then you have function of r here. Right? So there's two part of the function on this side. So you can use a separable equation, separating a separable equation technique. Okay. Yeah. So that you can solve using that technique. Basically, move the r over here, move the theta over here, then you integrate, you get the results. Okay. At the same time, right? At the same time, you could rewrite this one as this. Okay. So you can rewrite this equation just like that. And when you see this one in here, that's actually what? This is still first order. R is the output. And here there's no input, right? So this is basically the coefficient here for the r has nothing to do with r. It's all about theta. That's the variable, right? The independent variable of r. So basically this is a linear. Right? This is the linear equation. And here input is 0. So technically here is a homogeneous linear differential equation, or ODE. More precisely, is ordinary differential equation. Okay, and you can solve that as it is. It's essentially still separating variable to solve it. Okay. Okay, so sometimes it takes different formats, but you can use a corresponding approach to solve it. You get the same results. So that's about separable equation here. Okay, so let's look at. So here we have 1, 2. We looked at two different type of differential first order differential equation now. So let's take a look at the third type of differential equation. Now the name of the third type is a little bit confusing. Okay, the name of the third type is called homogeneous equation. Because this word homogeneous, we almost say it in so many different places, right? Because I actually just said homogeneous here, because that's homogeneous because the inputted here is 0. And now we have another name called homogeneous equation. As you can see later here, it's actually slightly different meaning. It's not slightly, it's completely different from this meaning here. But they all have the keywords homogeneous here, okay? So just don't confuse yourself. So what's homogeneous equation? Here is the definition. Let's say you have a first order differential equation at here. Okay? So given this first order differential equation, then it is a homogeneous equation. Okay, it's a homogeneous equation if this function f, xy, if this function fxy equal to function f lambda x lambda y, and lambda is a constant. And that's how the name homogeneous is defined. If the right side function f is the same as function f, but you change the x, y to lambda x, lambda y with arbitrary constant lambda. Okay. More actually, we actually call this fxy, we call it a homogeneous function of degree 0. Okay, so when you have a function f that can be written as function of lambda x, lambda y, we call this is a homogeneous function of degree 0. So basically here you can write a lambda to the power of 0, and here lambda to the power of 0 is 1. Now you probably wonder, okay, so is there a homogeneous function of a degree n? Yes, there are. Okay, I will write it down next, but let's take a look at this relationship here and understand a little bit more what exactly does it mean here. Okay, so for example, if we have a function fxy equal to xy over x squared over plus y squared. Okay. So if I have a function like this on the left side of this differential equation, and if you're required to solve this differential equation, the first step you wanted to do is to search, okay, so what type of differential equation is this a linear differential equation? Is this a separable equation? Right? Unfortunately, you look at this, you can't separate. You can't separate this into a function x and a function y. Right? You can't do that. And you can also see that this is not going to be a linear differential equation. Right? Yeah. And this one actually falls into the third type, which is the homogeneous. So why is that? So let's take a look at, if I replace the x with lambda x, lambda y, okay, we replace the x and y with lambda x, lambda y, let's just see what happens. So xy becomes lambda x, lambda y, and bottom here, lambda x squared and lambda y squared. And then you can see that on the numerator, on both the numerator and denominator, you got lambda square showing up. So you can cancel the lambda square. So you end up with the same as the function f of xy. So that's exactly the definition of this is a homogeneous function of degree 0. So similarly, you can exercise this. Okay. You can try this function. If you have another function f of xy that equal to ln negative 3x squared y over x cubed plus 4xy squared. So you have this function. And that's obviously not going to be separating x and y into two terms. And it's not going to be a linear differential equation, but you can verify. Okay, I want you to verify yourself. If you replace your x and y with lambda x, lambda y, it is the same as f of xy. So again, this is a homogeneous function of degree 0. There's a lot of terminology flowing around, but unfortunately, this one they just name it as a homogeneous. We can change that. Okay. Now, in general, okay, in this class we'll deal with just this case, homogeneous function of degree 0. But in general, okay, when you replace x and y with lambda x, lambda y, you could have a general case like this. So you can take the lambda, right, as a power term, lambda to the power of n. It depends on the actual function f. Okay. N can be 0, can be 1, can be 2. Right? So in general, you could have a result like this. So then f is called homogeneous function of degree n. Okay. So that's a general case. So we're going to deal with just n equal to 0. Okay. Yeah. In this class, just n equal to 0. But you should understand there's a general concept of homogeneous of function of degree n. Okay. So the question here is, how do we solve this kind of a equation, right? This kind of differential equation. If f can be written, or if f actually is a homogeneous function of degree 0. Okay. So that's the point we're going to look at it, right? So how to solve? So I'm going to use an example here to go through this solution. Okay. You know what? Maybe I should. Okay. Let's take an example here. Let's use an example to solve. Okay, here is a differential equation. Okay. On the left side, on the right side of the differential equation, you have a mix of x and y at here. Some conditions just to ensure that the square root term condition is satisfied. Okay, so underneath the square root, it should be a value greater than 0. Okay, that's what happens there. All right, so now let's solve this one here, right? If in an exam setting, I mean, if you have a first order differential, you have to identify what it is. Now, since we're learning this homogeneous function, a homogeneous equation, then this must be a homogeneous equation here. So let's take a look at, is this a homogeneous equation of degree 0 or not? So you can, so this one here is your f of x, y. Okay, you can certainly verify that f of lambda x, lambda y will be the same as f of x, y. Okay? Yeah. So once you verify that, and then we'll go through the approaches that we're going to do at here. So what we do now is this. For the term f of x, y here, we'll try to write it into the following formats. Basically, to write this f of x, y, okay, this function here, into a function of y over x. Okay, so that's what we're going to try to do. So how do we do that? So basically, how do we do that is, you look at this term in here, we're going to try to write as much as possible for all of the term, instead of x or instead of y, well, you know, we put it into y over x ratio. Okay. So let's take a look at this term here. Okay, let's look at how does that work for the current function f. So remember, we're trying to put things, okay, the terms into this kind of ratio y over x. So how do we do that? I mean, you know, for example, here, this x, or this, let's say this y at here, right? If you want to change this y to y over x, you need to divide by x. Okay? Yeah. But you do have x at here, so you already have it divided by x at here. So I guess initially you could just, right? That's y over x. Yeah, you put it into two fractions. Okay. So that this term you got a y over x now. How about this one here? Okay, so for this one. For this one, the x is outside the square root. I can move this x into the square root. So you get x squared minus y squared, then over x squared. And then inside this square root, so you can see you have 1 minus y over x squared. Okay. So now your function f, instead of just general function of x and y, so everything here is y over x now, right? Except the constant that you don't have to worry about it. Right? So this is a function now, y over x. Okay, yeah. So that's how you can manipulate the original small f function into a capital F function of y over x. So good? Yeah. So you can practice this kind of thing yourself. For example, let's say, just to give you a practice of this. If you have xy over x squared plus y squared, right? If this is a function, small function f, how do we write it into a function of y over x? So what do we do with this one? You basically will try very hard to change each one of the term into y over x. Okay. To do that, for example, this y squared, if you change that to y squared over x squared, so then it's y over x, right? So basically, you can do is you can divide both denominator and numerator by x squared. Okay. So then you get the bottom is y plus y squared over x squared, and the top becomes y over x. So overall, you have this term here, and the bottom here you have a y over x total y over x squared. Right. Again, here is a function of y over x. Okay, that's the first step you have to do to make it into this format here. Okay. All good? And then you let u equal to y over x. Okay, so we let the u equal to y over x. Introduce a temporary variable u. U equal to y over x means y equal to u times x. So that's naturally from this new variable u at here. Okay. So once you get this, this function f of y, capital F of y over x, can be the y over x can be replaced with u, right? Can be replaced with u now. If I replace with the u, then this function becomes y minus u squared plus a u at here. So your original differential equation, so the original differential equation becomes y prime equal to f of u. And this is your left side of that original differential equation. And in this case, this is your f of u, right? Yeah. So then what is y prime then, right? Y prime, we will use the relationship between y and u and x, because you introduced u equal to y over x. So we use this relationship for the y prime. So y prime at here is product rule. U prime x plus ux prime, and you get a u, right? Yeah. So y prime is this. So we get du over dx times x plus u, that's your y prime, and equal to f of u. Okay. Now, since you learn partial derivative, multivariable, you might actually argue, why is it the du over dx? Why not partial u over partial x, right? Yeah. But you can think of it this way, because you're trying to solve for y. And once you solve the y is function what? Of x. So when you define u equal to y over x, so u basically is a function of x. So then you can use du over dx at here. Okay? Yeah. So I'm going to replace the f of u with the actual expression. That's your actual expression for f of u. So you have a new first order differential equation. Now this time is in terms of u and x instead of original y and x. And this is actually quite straightforward now, because you got a u in here, and then you get a du dx at here, and fortunately we actually can cancel this u on both sides of the equation here. So you get du over dx times x equal to root 1 minus u squared. So can anybody tell me from here what technique can you use to solve this differential equation? Separable equation, right? So you can separate in the variable. Okay? Yeah. So you can use du over 1 minus u squared and x dx to move to the other side. And you get this one here, separating variable. Then integrate both sides of the equation. The first integral, okay, that's actually first year. So this one you probably you can use a formula if you. Typically, I'll give you this one here. So this is the inverse sine u. Right, the results of this one is inverse sine u, and here's ln x. Okay, that's a plus constant c, and then that gives us a u equal to sine ln x plus c. So now you get a u and an x, but don't forget your actual objective is to solve for y. Right? So what's u? U equal to y over x. So replace the u back with y over x. So we get a y equal to x times sine bracket ln x plus c. Okay, seems to be a very strange solution, but you got the solution, right? Yeah. If you have an initial condition, then you can solve for the constant c. Yes? Why is there a c here? Why not here, you mean? It's the same thing. You put a c here, move here, it's still constant. Yeah. Okay? Right, so this is essentially the approach to solve homogeneous equation. Okay. So let's go over this again. Okay, you do need a little bit of practice to get used to this. The key is to identify that this is a homogeneous type of equation, okay? Or to identify the function f is actually a homogeneous function of degree 0. To identify that, what do? We basically replace x and y with lambda x, lambda y. And if you find that it actually didn't change at all, right, to this function f, then you can conclude this is a homogeneous function degree 0. And once you identify this, the next step is to write this function f into a function of y over x. Okay. And to do that, you do need to manipulate. You may have to divide the denominator and numerator denominator by a common term. Okay, and manipulate things, move around, and you get everywhere y over x except a certain constant, which is 5. Okay. So once you get that, then you will let u equal to y over x. So as you can see, the only uncertainty is actually this step here, right? So this step you had to manipulate, you had to get it right. But from here forward, they are very standard approach. You let u equal to y over x, which means y equal to ux. Then y prime will become u prime x plus u equal to the replaced function f of yx, become f of u. Most probably you get over a u. If not, then you move the u to the other side. Okay. Then you use the separating variable technique and to solve for u. Once you get the u, replace the u with y and x, and you get y. Okay. So that's a general approach for homogeneous type equation. But then again, you have to be careful. This is not the homogeneous we're talking about for the other case, right? Yeah, this is just the name. There's some redundancy at here. Okay? Yes. All right. Any question for it? Okay. So I think I don't need to dwell on this for too long, and this is not a really difficult case. You just have to get used to this. Okay. This is a third type. Okay, the third type of differential equation. So let's take a look at the fourth type. The fourth type is called exact differential equation. Exact differential equation. So let's consider this differential equation. Okay. So maybe I'll start like that. So let's consider this one. dy over dx equal to a function of x and y, and then divided by another function of xy. Okay. So let's say you have this one here, and then you can rewrite this, okay, into. Actually, sorry, I need a negative sign here. Okay, just put a negative sign for my ease of writing. Into pxy times dx, and then plus qxy times dy. So you can write it into this format. So overall, this is still a first order. Okay, this is still a first order DE differential equation, and you can certainly manipulate that into this. Yes. Oh, dx. Yes. So p of xy times dx plus q of xy times dy and equal to 0. So far, if you look at this one, it seems to be actually quite different type of a differential equation. Okay. However, okay, for this one, there's a very special case that will make it easy to solve. Okay. For certain cases, okay, the left side, the whole left side, okay, is let's just describe it. For certain cases, we can find a function f of xy. Okay, we can find a function of f of xy such that df equal to this. Does that look strange to you, or does that look actually familiar to you now? What does that remind you, or what does that not remind you anything? Not a partial? Total differential. So what we have here is a total differential here, right? So basically means if we can find a function f such that its total differential equal to this whole thing, which basically means what? What is the function of p? Function p, according to the total differential formula, it is partial f, partial x. What is the function of q? Partial f, partial y. Right? There's a nice connection right here between this course and that course now. So if you can find a function f, and such that this function's total differential can be written into this format, and the two partial derivatives of this function f are exactly a function p and a function q. Okay. That's going to make our life much easier to solve this one, and you'll see why. Okay. So you see, we started from this. Okay, we started from this and written into this format, and then we asked the question: is there a function f such that we can do this? Right? We asked the question if, and of course, may not be answer may not be yes. But if yes, if there is a function f, we can do that. Then what does it mean? Basically means your original, you see that here, your original differential equation, which is this, equal to 0, right? So the original one, the original DE, what does the original DE becomes now? If the answer is yes, you find the function f, and you take the two partial derivatives, which give you the p and q. Now the original differential equation becomes, what does that become? This whole thing becomes what? df equal to 0. So when you get a df equal to 0, what do? You integrate, right? You can always integrate. So basically it means you will get a solution f of xy equal to 0. So df equal to 0 meaning, what is a derivative? This is differential. What's the differential of a function equal to 0 means? Or what's the derivative function what's a derivative function equal to 0 means? That function must be constant, right? Must be constant. So that's why you get this solution here. And this is your solution for, essentially, for this original differential equation. Okay? That's why it makes things much easier if you actually can find a function f to do this. Right? That's why it's become easier. Okay. Okay, and of course, the next logical question is, how do I know, right? Yeah, how do I know that? Okay, but before we answer that question, let's take a look at an example. Okay, yeah. here is a differential equation, first order. We write it, okay, in the format of p of xy times dx plus q of xy times dy. Okay. And for this differential equation, okay, without telling you how we get this, okay, and I can tell you that, okay, we can find this function f that equal to x cubed y plus 1/2 x squared y squared. Okay, so we can find this function f such that if you check it out, okay, partial f over partial x, okay, if you do a partial derivative of f over x, you get this function p. And if you do the partial f over partial y, and you get this function q. So mysteriously, this function f just dropping down from the sky, and you look, oh, look, beautiful. Okay, so now what's the solution for this differential equation? So the solution for the differential equation, you can just immediately write it down, is x cubed y 1/2 x squared y squared equal to c. That's it. Okay, right? So things much easier if you can do that. But of course, the next question is, how do we know that we can do that, right? And if we know we can do that, then how do we find this small function f? Those are very important questions. But I won't answer the question in this class. I will answer the question in the other class. Okay? So when we learn a different concept in the other class, we actually will have a very similar situation, but not solving differential equation. Okay? A different scenario, but the same two questions. How do I know we have a function f to get this two partial derivative equal to p and a q? If I have a p and a q, how do we find the function f? So this is a question here, okay? That's the first question. If f exists, how to obtain this f from p and q. Okay. All good? Yeah. So to save myself a little bit of time, just remember, okay, the answer will be given later in 248 class. Okay. But for now, you can just remember there is this type of exact differential equation that can use this approach to solve it. Okay. But it kind of hinges on these two questions. Okay. Any question so far? Okay. All good. All right. So we'll see you next Thursday.